Good morning, everybody. Today is Monday, March 30th. It is the official first day of fourth quarter. So this will be our first video and assignment going into fourth quarter. I want to thank you guys, especially you guys are really my only class that so far has got all of their work turned in. I really appreciate that. That obviously makes this whole thing significantly easier when you guys are taking care of things on your end and I'm able to just sort of teach to the best of my abilities in these videos on my end. So I really appreciate that. We're going to dive back into chapter 3. We just kind of got it started last week in terms of applying the first derivative test to see when a function's graph, or to sort of analyze the graph without actually punching the equation into a graphing calculator. So just to kind of get back where we were last week, if you take a polynomial function, in this case 2x cubed minus 3x squared minus 36x plus 14, we can generate a lot of information about the graph of this by just simply applying and looking at its first derivative. So if we do that first derivative test, we find the derivative of this guy. It's obviously 6x squared minus 6x minus 36, technically plus 0. And basically, it's just simple using the simple power rule. So what we end up with is this. The first derivative, or the derivative of that function, and this is kind of what we've been saying ever since we got into derivatives, is it's the slope function. It's the function that will tell us the slope at any point on that graph. So what we were looking at last week was this. If we don't want to just look at the slope in general, but if we take this and we figure out where the critical numbers are, okay, when is this function going to actually equal 0? Because if you think about it, if this is the slope function and the slope equals 0, the slope of a line having a slope of 0, specifically a tangent line having a slope of 0, means that it's a horizontal tangent line. So horizontal tangent lines only occur when a graph is peaked or valleyed. So when it's at a maximum or minimum, okay? So if we set this equal to 0 when we solve for x, what we're doing is we're just solving a quadratic equation. We can solve this by factoring. We can obviously factor out a 6 from all of this to make our lives way easier. We get x squared minus 1x minus 6 equals 0. Okay, so when I factor out that 6, I can then divide it away, so it literally is gone from there, and it's also gone from there. So what we end up with is this: x squared minus 1x minus 6 equals 0. We can factor this further and then apply the zero product property. X squared breaks into x and x. The factors of negative 6 that add to negative 1 would be a negative 3 and a positive 2. And that's 90% of our work, but not our answer yet, because now we just have to ask ourselves what x values would apply to the zero product property here. This is x equals 3, because 3 minus 3 is 0. 0 times 5 is 0, because if you plug in 3 for that x, it still wipes it out. So it's 3, and it's negative 2, right? Because negative 2 plus 2 is 0. It would be negative 5 times 0 is still 0. So here's basically what we did last week, okay? Is we said these are our x values of our critical points. Those are our critical points right there. So along our graph, or what we did was we split our domain up into separate areas. So we went from negative infinity up to our first critical number, which was negative 2. And then we went in between, in this case, these two critical numbers, from negative 2 to positive 3, and then from 3 to infinity. So what we said last week is for every critical number, it's going to split the domain into one extra portion. So there's two critical numbers, there's 3 different domain areas. And then what we do to determine if our graph is going up or down is we pick a test number in this region and we plug it back into the derivative, okay? So obviously here we could plug in negative 3. In this interval, I'm always going to take advantage of plugging in 0 when I can, and then over here I'll just plug in 4. I'm just going to pick the smallest number in each domain. Negative 3, 0, and 4 are my test numbers, and if I plug them back in to my derivative here, And it really doesn't matter if I plug it into this one, the 6x squared minus 6x minus 36, or its equivalent one. But we'll just go back just to be thorough. We'll plug it into the original one. So when you plug negative 3 in, that becomes positive 9 times 6. That's 54. Plus negative 6 times negative 3 is positive 18. That's why I put plus. And then minus 36. And all we really need to recognize here is this. 54 plus 18 minus 36 is going to be a positive number. So that means that in this interval, from negative infinity up to negative 2, along that whole interval, I'm going to have positive slopes. So that means it is an increasing function. Okay? It's increasing over that domain, which means in all likelihood, it's probably going to decrease here. But 0 is an easy enough number to plug in. When you plug in 0, you get 0 minus 0 minus 36. So obviously that's a negative 36. That's a negative slope, which means the graph is going down or decreasing. So in this interval, it's actually decreasing. For positive 4, when you plug that in, 4 squared is 16. 16 times 6 is 96. So we get 96 minus 24 minus 36, but that's still going to stay positive. 96 minus 24 minus 36 is still some positive number. So you got a positive slope, which means your graph is going back up. Okay, that's what we did last week, right? What we're doing today is we're basically taking this the next baby step forward, okay? All we're doing now is we're kind of identifying and discussing the critical points. Instead of just talking about the nature of the graph between the critical points, now we're actually talking about the critical points themselves. So what actually happens on the graph at negative 2? Well, if you think about it, if the graph is increasing from left to right all the way up to negative 2, or all the way up until you get to negative 2, and then after negative 2 it starts decreasing, that means the graph's going up, then it goes down. So what is negative 2? That would be a maximum. That would be a relative max. So here's what we do. Like I said, this is just the next baby step beyond what we did last week. Now we just talk about what these two numbers next to each other would mean. What is a positive number and a negative number, an increasing graph, and then it turns into a decreasing graph? What does that mean happens there? It means the graph maxes out. There's a relative max at negative 2. But here's the thing. We don't just say at x equals negative 2. We get the actual point for the function there. So if you plug negative 2 all the way back up into your original function right here, that's how we get its actual coordinate, right? We're not plugging negative 2 back into our slope function. We're plugging it back into our original function to get its actual point. So if you plug in negative 2 for all those x's, I've got it worked out off to the side here, you get 58. Negative 2, 58. And then basically we do the same thing over here at 3. We plug 3 back into our original function, and you get negative 67 for your y value. But now think about it. At 3, what's happening? Well, the graph's going down all the way up to 3. And then once you get past 3, it starts going back up. That means it minimums, it bottoms out there. So we say that is a relative minimum at that point. So if we're just thinking about this, we could kind of graph it. We don't really want to because of the huge numbers. But if we're thinking about it, here's my critical points. There's negative 2, there's 3. At negative 2, 58, pretend that's negative 2, 58. There's a maximum right there. At 3, negative 67, there's a minimum there. And if we just kind of splice these two things together, we said our graph is going up or increasing from negative infinity to negative 2. So that means the graph is going up there. At negative 2, it maxes out. So then it starts going back down until you hit 3. Then it bottoms out. All right, it's a minimum at 3, negative 67, and then from 3 to infinity, it starts going back up. So there it is. okay? Like I said, all we're doing is we're taking this one step further and identifying the actual point at that critical value, the actual coordinate, by plugging it back into its original function, and then just doing the obvious thing of stating the obvious. Is it a maximum or is it a minimum? Those are the critical numbers because their tangent lines would be horizontal, right? That was the whole like setting it equal to 0 and solving for x. And now we're just taking it this one step further. By the way, the reason these are called relative maximums and relative minimums is they're not the absolute highest point on the graph or the absolute lowest point on the graph, because these graphs in this direction goes down forever and in the other direction goes up forever. So there is no absolute minimum or maximum. These are just relative mins and maxes. Okay? That's it as far as the work that we're going to do today. So I'm going to show you one more example of this, okay, just to hopefully solidify the understanding, and then I'll get you the assignment. So here's a different function, f of x equals 3x to the 2/3 power minus 2x. And the directions, regardless of what the directions ask, I know for part of the assignment today it says use the graphing calculator. Obviously you're not doing that. You're going to just do exactly what we're doing here. So what we do is we find the first derivative to get our slope. So here 2/3 times 3 is 2x. The 3's would cancel. But then you subtract 1, you get negative 1/3 power. And then the derivative of negative 2x is just negative 2. If we turn this, because this derivative has a negative exponent, so if we turn this into a fraction, move the x to the bottom, here's what we get, 2 over x to the 1/3 power minus 2. Okay? Finding the critical numbers now of this. The most obvious critical number is anytime you have a fractional derivative, the denominator being equal to 0 is going to give you a critical number. So obviously 0 itself is a critical number here. X equals 0. We'll find our critical numbers. Write them over here. So 0 is obviously a critical number because 0 will give you a domain error here. The other thing that we always have to do though is this. Most of your assignment today is just simple polynomials. So when you find your derivative and it's a simple polynomial, you need to set it equal to 0 and solve for x. Okay? It's not only that the critical numbers aren't only the ones that make your fraction not make sense, it's also the ones that make the entire derivative equal 0. So if we just think about solving this for x, you're going to add 2. You get 2 over x to the 1/3 equals 2. To clear this denominator, we have to move it to the other side by multiplying by it. X to the 1/3, x to the 1/3. Those cancel. You're literally left with 2 equals 2x to the 1/3. Divide both sides by 2, you'll get 1 equals x to the 1/3. And we're fortunate that it's a 1 because x to the 1/3 is the cube root. But obviously what number, when you raise it to any fraction, is going to stay a 1? It's obviously 1. So my other critical number would be a 1. So we do the exact same thing that we did last week. Let me make sure you can still see this. You split your domain up according to this. So my domain is negative infinity to 0, 0 to 1, and 1 to infinity. Just plug in negative 1, plug in 2, and then unfortunately here we'll have to plug in a half or a fraction. So it's a little bit weird, but when we plug this in, when you plug in negative 1 into this derivative right here, negative 1 to the 1/3 power is still negative 1. So this is 2 over negative 1, which is negative 2, minus 2 is negative 4. So we have a negative derivative. When we plug in negative 1, that means our graph is decreasing from negative infinity to 0. It's going down. When we plug in a half, I mean, you can basically do the work here. If you plug it into your calculator, 0.5 raised to the 1/3 power, I'll get you, grab my calculator just so I can show you the actual number. .5 raised to the 1/3 power is 0.79. So if we just kind of think about that, this is 2 over 2 divided by 0.8, let's just round it, is 2.5, minus 2 is positive 0.5. This is going to give me a positive slope, which means my graph is increasing. And then for once we hit 1, if we plug in 2, again, we would just basically plug it into our calculator. 2 raised to the 1/3 power. 2 raised to the 1/3 power is basically 1.3. So 2 divided by 1.3 is 1.5. 1.5 minus 2 is a negative number, so it's decreasing. The only extra thing that we're going to do today is we're going to identify what these numbers mean, what a decreasing to an increasing to a decreasing graph means. So if the graph is going down and then it goes up, so down, up, that means this is a minimum. That is a relative min, at, and then we actually get our coordinate. So you actually plug your critical number 0 back into the original function. Well, if you think about it, plugging in 0 into the original function will wipe out the whole function. It's 0, 0. It's the origin. There's a minimum at 0, 0. And then obviously this represents a max, relative max at 1. But to get its actual value, we plug 1 back in. So right here, if you plug in 1 for both of these x's, it literally becomes 3 minus 2, which is 1. So you have points or critical points at 0, 0 and 1, 1. 0, 0 is a relative minimum. 1, 1 is a relative maximum. Okay? So hopefully that's somewhat clear. Like I said, it's sort of just the next logical thought after finding what these graphs are doing in between and on both sides of the critical numbers. Then the next thing to do is talk about what that means about the critical number itself. If it's a minimum or a maximum, or it's possible that it's neither. It's possible that it's a point of inflection. But in this case, we really won't see that too much. Okay? So let me know if you have questions. I'll do my best to answer them, probably just over email. And then we will be continuing on in section 2 on Wednesday. Okay? Hope you guys have a great Monday, and we'll talk to you later.